Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at the changes of Gibbs free energy with pressure. So we introduced this idea a little bit last time that we can go ahead and look at the changes in Gibbs with respect to pressure using the fundamental equation. So again, this case, we're going to ignore the temperature changes and really focus in on this relationship of Gibbs and pressure. Now, specifically because we like working with size-intensive properties, we're going to use molar Gibbs and thus molar volume. That way we can go ahead and look at things more on a comparable basis across different materials. Now, what this allows us to do is if we know the Gibbs free energy for a given state, we can go ahead and find it for that different pressure by literally just applying the integral of this molar volume over pressure. Now, part of the issue here is that this molar volume will often have a pressure dependency. So how we go ahead and evaluate this integral is very much going to depend on what state of matter we're looking for. This is going to be a rare case where the simpler case is going to be starting to look at condensed phases. So condensed phases is just a fancy way of saying liquids or solids. So again, where we'd have that incompressibility, where the changes in pressure shouldn't change the molar volume that much. At this point, I should be able to assume the molar volume is constant, at which point I can go ahead and pull it out in front of the integral, and I'm just left with the simple idea that the final Gibbs is just going to be the initial one plus the molar volume times the change in pressure. Now, ideally, this will be a nice, simple relationship. In reality, we're going to find that the volume will actually decrease a little bit with pressure. But as long as we're looking at relatively small changes in pressure, so worth noting, under about 1,000 bar, we can consider the molar volume being relatively constant, and this works fairly well. However, once you get to true geological or industrial scales, you may have to go ahead and consider that volume change. This is going to be the point where looking at some of our expressions and how we can combine our expansion coefficients and isothermal compressibility. That will help us get this molar volume dependence. So again, we do have some ways to go after this. Now, what is the increase? Let's go ahead and try and look at how this Gibbs free energy will change for a couple of common substances. So what would I expect to be the relative change in Gibbs free energy if I increase the pressure from 1 to 2 bar? This is pretty much the same as 1 atmosphere to 2 atmospheres. So I literally double the pressure for a set of common substances. So we've got water, which is a molar volume of about 1.8 times 10 to the negative 2 liters per mole. Graphite and diamond, both of which are going to be a little bit more dense, so a little bit lower molar volumes. Now, in this case, let's start with the water. I can get that change in Gibbs by simply taking the molar volume times the change in pressure. Well, the change in pressure here is just 1 bar, so that makes life easy. And the molar volume is just that 0.018 liters per mole. Now, notice here we have a fun bit on units. Because we go from liter bar, but we want energy, so we want joules. This is where we can use a common rule of thumb that 1 liter bar is 1,000 joules, meaning that we just multiplied this number by, or sorry, is 100 joules, which means we can multiply this number by 100 and we'll get the value in joules. So this is a nice feature of using bar. So it turns out that for every bar of excess pressure I put onto a system, I'll increase the energy of the water by about 1.8 joules. Now, it's worth noting, this often is considered a relatively small amount and should be relatively ignorable for most cases. This is one of the reasons why we can generally consider the free energy of a condensed phase to be relatively invariant to pressure. Now we can do the same thing for graphite, where again, we're just going to multiply this value by 100, and we end up with about 0.8 joules. So we have even less of an influence for graphite. And diamond, which is very dense, it's going to be about 0.5. So again, in these cases, yeah, it's relatively safe to say that, first of all, this relationship is going to be fairly good. molar volume isn't going to be changing much, but we're not really ending up changing the energies that much. Enough that if you're paying close attention to your equations, you might have to consider it. But most of the time, this is going to be relatively safe. But it is worth noting that once we get to condensed phases, we often have changes in pressure that are much more extreme than we'd otherwise expect. So what would happen if I increase the pressure not by 1 bar, but by 1,000 bar? Now, this might seem a bit much, but this is not unheard of when you're talking about either industrial settings or especially if you're looking at geology. So geologists are very interested in this relationship. Now, what we can do is, assuming the molar volume doesn't change, we can now, instead of just multiplying the system um, by 1 times 100 for unit conversion, we can multiply it by 1,000 times, again, another 100. So we're seeing 100,000 times that value to get us into joules. But in common parlance, well, instead of looking at joules, we can just look at kilojoules. So that means that if I apply 1,000 bar of pressure, I've made water 1.8 kilojoules per mole less favorable. And this is going to be enough to really change some physical properties. We can do the same thing with graphite. Now notice we've reached about 0.8 kilojoules, and for diamond, 0.5. Now again, these are enough to start to slowly change the stability of matter. And again, this plays a major role when we're looking at geological systems. But notice these energies are still relatively minor, with again the idea that about 1 kilojoule is about 1 order of magnitude of favorability. So again, enough to really play a difference, but notice we have to hit pretty high pressures to make a condensed phase change. Now, it's worth noting what we're often really going to be looking at isn't so much these absolute Gibbs free energies. We're going to look at the relative changes in Gibbs. So what I'm often going to care about is how the pressure can affect some sort of phase transformation. So in this case, like always, we can go ahead and just figure out, okay, what's the difference in energy from the product and the reactant at this elevated phase. Now you can do the most common phase that phase transformations we often have to worry about this for is often going to be things like going from liquid to solid to liquid, so that free energy of fusion. But I like shiny things, so we're going to look at what happens if I apply excess pressure to going from graphite to diamond. And again, note that graphite's the more stable form under room pressure, but diamond forms under high pressure. Now, to do this, we can use very similar rules that we did for Kirchhoff's law. I can go ahead and do the energy correction for both the product species and the starting material independently. So we're going to add the correction for each one independently. So how that change in pressure changes the free energy of the diamond and the graphite. We can then insert in these expressions, and what we're left with is the standard state conditions for both my product and my reactant. But more importantly, we're often looking at the difference in between the molar volume of the product and the molar volume of the reactant. Now, rearranging this expression, again, we now have the difference in free energies of the products, or the difference in free energy at that initial pressure, and we have the difference in molar volumes and the pressure. But since that pressure term is shared, you'll notice, again, this looks very similar to Kirchhoff's law, where the difference in free energy at the higher pressure is going to be the same as the difference in pressure, or the energy at the lower pressure, plus this corrective term. But now instead of being the difference in heat capacities, it's the difference in molar volumes. Now again, if we're looking at the transition of graphite to diamond, well, the difference in molar volumes is about 0.003 liters per mole. That means that if we turn this in terms of joules, it means for every bar I increase the pressure, I will favor forming to graphite by about 0.3 joules. Now, this means if I put a couple bars of pressure, I am not drastically favoring the formation of diamond. But if I start working my way to really high pressures, so starting to get to the kilobar range, Now we can actually see diamond becoming a lot more favorable as we're now talking about kilojoules of energy. Now, this is all for the relatively simple state of condensed phases. So going from condensed phase to condensed phase. Now, if I'm looking at gases, we have to be a little bit more cautious. Because if I'm looking at how the favorability of a gas changes, well, again, we still have the same general expression. But the difference is now this molar volume term has a real pressure dependency. Now, if we're looking with gases, we're usually going to assume an ideal gas, so we can go ahead and insert in the ideal gas expression. So the molar volume can be replaced by RT over the pressure. Now, we've got the integral of dP over P from initial to final pressure. So this is just, when we do this integration, this will just give me the natural log of initial to final pressure. Again, noting that RT came out in front. So now we get a very common form where the difference in Gibbs free energy is just going to be RT times the natural log of that ratio of pressures. Now, most commonly, our reference pressure is going to just be standard state conditions. So one of the most common ways we're going to use this is if I want to go ahead and figure out the Gibbs free energy of a gas at any given pressure, I can do so by starting with the standard state pressure, or 1 bar, times RT ln of that new pressure. Because notice that standard state pressure is 1, so this is mostly just going to provide the units. So you can literally just add in this RT ln P to figure out your pressure correction. Now let's go ahead and apply this correction to some real ideal gas systems. So notice that when we're taking this integral, what we're really doing is integrating this odd volume versus pressure term. Now, what this means in terms of the molar Gibbs is that we're going to see more or less an exponential relationship in that as we go ahead and increase the pressure, it will eventually level out till it's not really changing. As we decrease the pressure, it will change drastically going down. Now, what would the free energy change look like if I was going to again double the pressure for one of our most classic gases when we're dealing with industrial systems, steam, because we love a good steam engine. So if I go ahead and take the pressure from 1 bar to 2 bar, well, that's just going to be RT ln of 2. So notice that brings us to about an increase in free energy of about 1.7 kilojoules per mole. Note, I had to increase the pressure of water by 1,000 bar in order to get that same influence. So we have a much larger response in terms of free energy when looking at gases. So oftentimes, if we're going to be looking at a comparison of a gas to a solid, we'll assume that the solid's free energy doesn't change that much, and it's mostly being dominated by this gas component. Now, in comparison, what happens if I increase the pressure from 1 bar to 1,000 bar? So if I have that 1,000 bar increase, note that because we're going through a natural log term, we only have a 10-fold increase. So again, where you have that linear scaling in solids, but a much smaller amount, you have this natural log scaling, which will level off to high pressures. But it means that if we go in the other direction, you'll see a much bigger response. So some things to keep an eye out for on the systems. But generally, if we're looking at pressure dependence of a system, we're going to be paying much closer attention to the gases than we will to the solids or liquids. So next time, we're going to be diving into the free energies of gases and figuring out, well, what do I do with this expression if I don't have an ideal gas? Next time, the return to real gases as we talk about fugacity. Until then, take care.